Good afternoon. Thank you, Kurt, for having me here. Actually, when I saw the topic of the presentation, on-site energy production, I was a little surprised that I was in this category. As Kurt said, I typically work in sustainable building design, and we are looking at the design process of a building, actually. So we're developing a lot of tools of how to make energy-efficient, comfortable buildings possible during the design phase. So the one link that I see, and I wish to show you this, designers need their pretty pictures, so I'm kind of a little at all. So why? So I, of course, want to make a case, well, first of all, that energy, that buildings are important, and I'm sure you've seen a lot of slides on that already today. In the US, buildings are responsible for about 40% of carbon emissions, and since we have some Germans here, as Goethe said it, you can make mistakes but should not build them. So there's a strong argument why you should actually look at buildings explicitly. What I'm going to show you is the slide of LEED buildings, of the first generation of 100 LEED buildings that we have data for. And when you will imagine a slide, you basically see a slide with the energy use of 100 buildings, and people have started to pair the energy use of these buildings with a typical building in the US. And what one, of course, would expect is that the LEED buildings, LEED being a green building rating system, would use considerably less energy than the regular US building stock. But when you actually, and overall, this is true, LEED buildings use about a third energy less than that regular counterparts. Yay! But so this is where I am. So these are the. I have a remote. So this is where I am right now in yellow. In orange, you see here 100 LEED buildings. That's the first generation of LEED buildings. The EUI energy use per square meter, and in black you see always paired the typical reference buildings linked to that. So if you have an office building in the northeast, we compared another office building of similar size to that. And what you would love to see is a lot of black sticking out, because that means that the reference building uses more energy than the LEED building. But what you actually see in a third of the LEED buildings, that actually their typical reference building uses less energy than the LEED building. So that's a real problem we have. So how can we address that better? Well, it's something that has been recognized by now. When you just look at the numbers of registered LEED projects that the USGBC has been performing, you see this peak in 2009, and of course then the crash hit. But in black you see the LEED certifications for new buildings, and in orange you see for commissioning and maintenance. So actually you see right now that the amount of projects that receive careful detail of how the building is actually commissioned is nearly as big as the projects that are newly certified. So that's a good sign. Also, I come from the building design world. We are creating energy models early in the design process. So we are basically modeling buildings, doing the design, and say this is how you should put a building together, integrated design to have it energy efficient. So one could ask the question, why don't we use that during the actual design process while the building is being used? So here what you see is the same LEED buildings, and you see here the simulated energy use during the design process and the actual energy use. And if our product was perfect, you wouldn't see any dot, because everything would be hidden behind the black line, which isn't the case. So you have specifically big institutional buildings tend to have problems. And we know why this is the case, because you can't really expect that while you're designing a building, you know exactly how people are going to operate the building and what they're going to do with it. But the happy news is, this is a slide from NR Modal, a Canadian consultancy firm. They're actually using their consulting design phase model doing the commissioning of the building. And here you see for 40 buildings in green, you see the energy use of these Canadian buildings. In red, you see the reference energy use. So green is lower than red. That's a good thing. That means they're saving energy. But even more so, the blue dots indicate what their energy models predict. So they are basically able, with their energy models, to track pretty well what their buildings are actually doing. So that's a good sign. We try to do something similar. And we just wondered, well, what would happen if we did that to a very regular building? And as a regular building, I picked this building. This is the Graduate School of Design from 1970. Not a very energy efficient building. It's a modernistic icon, but we just wanted to see how can you model something like this. So in a seminar a few years ago, just with a couple of students, we put a weather station on the roof, we measured the building, we spied on everybody in the building to see what they are doing. We compared that to the energy use of the building, And this is what we got for electricity, heating, and cooling. So you see the measured and the simulated energy use. And we were pretty happy that we got for heating and electricity very close, but we were pretty off for cooling. And of course, at first, we were blamed that was our fault. But I kept insisting that I think our model is right. Something seems to be wrong with the building, actually. So we looked at 3 years of cooling data for the building. And then in 2008, suddenly they got a jump in cooling demand. And they paid $100,000 more a year for cooling without really being able to justify it. And that happens all over the world. There were some questions, of course, being asked. But in the end, for these really complex buildings, you don't know how much you have to pay to maintain them. So then, after being insistent in the pain, this is the energy use for over 2 years for cooling of this building. Then they finally switched the meter for the 3rd time, and then miraculously the line went down, so that saves the school now every year $150,000 in cooling. And that just shows you when you start implementing this type of tracking, you can maintain your building stock a lot better. So this was just the start. So what are we learning from this? By really understanding what our building is using, even if we don't have any green buildings, we can generate a lot of savings if we know what to concentrate on. So the next step might be, so we have this tool right now with which we can track and control buildings. What does that mean when we look in the future? Is that a big effect? So of course there's this trend, at least in my field, to say when we are designing a building right now, forget what the climate is now. I want to design my building 50 or 80 years from now, and how you can do that. So there's a technology called morphing, where you directly link to global general circulation models from the IPCC. You use your current weather data, but you basically tweak your weather forward 50 or 80 years to see what the weather is going to be then. And that's a really big effect. So here you see this calibrated model from Gantor that I showed you before for heating and cooling for now. And here we are basically turning the wheel to 2080 forward. And this is not one of the extreme storylines. This is one of the storylines from the IPCC that's middle of the road. And you basically see we will be using 36% energy a year less for heating and 45% more for cooling in this climate here. So this is a gigantic effect. If you think about it, this is our building stock here and all over the world. We're going to basically have buildings that have to deal with a completely different climate. And if we are able to plan for this right now, that's of course helpful. So all these natural ventilation systems, I think we have to consider putting hybrid systems in place, something to take this into account right now. Well, if you're a little cynical, you can say as an owner, well, it's kind of academically nice, but who cares? How does that really affect my bottom line today? And that's, of course, a key point, because we want to justify financial decisions today. So what we've tried, this is a master thesis from Seth Holmes. We tried to combine these climate change models with government predictions of price developments in the future. So once you do that, and that takes a lot of tinkering, but once you're doing it, you're basically able to predict the future, not only in terms of energy use, but in terms of money. And when you do that, then you can be a lot more specific and concrete. So imagine you are owning one of these boring office park buildings in Waltham, and tenancy is low, and you're thinking of renovating it, and you wonder how much should I invest in the building. So if you have, this is your base building, if you just bring it up to code in Massachusetts, that would cost you $90,000. If you would do a little more solar shade, a little more ventilation systems in there, you are at $180,000. And if you do some more advanced techniques, you're at $250,000. So is that worth my money? So here what we've been looking at, basically, the black curves show you what you would predict if you wouldn't take climate change into account. Then you would say, well, in the base case, my building is going to cost me $1.5 million over the next 60, 70 years. Compared to just under $1 million, is it worth this or not? Of course, the moment when I take future prices and climate change to account, I have two changes. It's going to get warmer, so I'm going to need more energy. And then, of course, depending on how much warmer it gets, my energy price might go up. So you see that right away translating into now $2.3 million and a very large uncertainty related to that, because, of course, we don't know what the climate is going to be. But the big advantage is when you have an energy efficient building that works with the climate, then it doesn't matter what the climate is going to be. Your uncertainty, your investment, your risk is pretty small there, actually. So this is pretty nice for layman people. Of course, when you talk with anybody who has money to spend, they are looking at the internal return on investment. Because if I own this building and I have $250,000, I might as well invest it at Wall Street. So what you see here is basically the conversion factor. This is how much internal rate of return you would get out of this. And that's really interesting because there's a lot of interest right now in the business world in investing in energy efficiency measures, but there's not a lot of trust that people will see their money back. And I guess with this type of analysis that is helping them to make these decisions. So finally, as 3 minutes, I can make it in 3 minutes. So as Kurt said, we are expanding this right now. It's nice to do this on a case-by-case, building-by-building level, but we really want to go to the whole city. So I skipped that. Why a building's important. What we're doing right now is we're basically using Cambridge as a sandbox. So we have a really detailed GIS model where we have a frightening amount of information about every building in Cambridge, and that's in this country publicly available. And when you do that, we have this detailed model of 17,000 buildings, and we can combine this with LiDAR data, so we can basically build three-dimensional models of the whole city. And our first exercise was just to do a solar map of this. So what you see here is a very detailed 2-foot by 2-foot resolution solar radiation map of the whole city. And so at the beginning of September, this is going to be released. We worked with the city of Cambridge and with Modern Development Studio to do a nice interface. So you can basically Google your address and you can zoom in. And you see the parts of your roof that have a high PV potential, taking self-shading into account, what the previous speaker has alluded to, including multiple reflectances and so forth. And we have a little calculator here that takes all state incentives and so forth into account. So you very quickly see how if it would be worthwhile to put a PV system on your roof, for example. This is actually pretty easy to do, so we are really more interested in using all this data to auto-generate lead-type models for every building in Cambridge. So then we'll be able not only to say how much radiation falls on your roof, but also, well, we are predicting this is how much energy you should be using. How much do you actually use? Well, maybe forget PV, you should maybe do something else before you're investing in that. So for this method, we are developing this urban development interface right now, which we hope to release in half a year. We've already used it for teaching, where you can basically do massing models of cities. You can model 100 buildings at the same time for energy use. Then you can do walk scores and basically see how walkable is my city around this and how much daylight get in the whole city. And the point is really to empower architects and planners to make this decision early in the design process itself. And this is just a very fun, I know, probably 1 minute left, one application from last year. These were 3 students from Spain that took the class, and they looked on the development of the expo site in Seville and in how far if one should do a tabula rasa and just rate the whole thing and do a low energy development, or do retrofitting infill, what makes most sense? So it's a really basic questions. And they tinkered around with our tool of basically how do I arrange my buildings, what makes sense from an energy efficiency standpoint. But then they put it together, how much embedded energy do I have in my buildings? What does climate change do to me? And how much energy am I using overall? So this is really becoming interesting because you see here, this is embedded energy for different scenarios in construction, in operation, and the operation becomes steeper and steeper due to climate change. So you can really say, what are the break-even points if I do these things? And of course, as one would expect, a tabula rasa approach where you basically get rid of everything doesn't make any sense. We need to work with the building stock that we currently have. And even though that's probably plausible to a lot of people, it seems to be necessary to show people that numbers to just bring that message home. And knowing that I'm out of time, I thank you.